Recorded is rolling. It is Tuesday, March 10th. So we're going to do animated slides, review, and notes. Uh, yeah, so all these posters we got and the thumbnails for you guys, I finally got those animated and I uploaded that file to Google Classroom. Here, I'll point it out to you guys exactly where it is here. So, I do highly recommend you guys go download this. It's right up. There's announcements. All right, and we are back. We are back. All right, so guys, go download this, and actually, we're gonna try this today. We're gonna be going through this. All right, so let's go back to the beginning of kinematic motion, and a lot of these topics. How'd you guys start with labs? Right, so you guys got to get your hands on the equipment, materials, and see how do things actually move, right? And record a bunch of data, and that led to a bunch of equations. So carbon inclined lab, guys, this is one of the big ones. One of the big ones here. Oh no, is this not? Hang on, hang on. I got the wrong. Okay, pause right here. All right, guys, go ahead and draw axes for those 7 graphs right there. Go ahead and draw those 7 graphs. All right, everybody chance in your notes or the paper that I put on your desk. Okay, I'll walk you guys through one by one. Make sure you guys know what those graphs look like and why. Right, so when you guys did this lab, remember you guys were in different experimental groups. Okay, so there are a bunch of variables or potential variables. I mean, you guys can see them there. Okay. Right, so we've got how far did the car roll in meters. We got how much time passed in seconds. We got how fast was the car going meters per second. You guys remember having those speed gates? You can get an instantaneous speed. Okay. The mass of the car. Right, you guys were measuring all those. I think the only variable up here you guys were not directly measuring was this acceleration, but you guys know enough physics by now. I think you guys can know what that graph should look like too. Right. So everybody getting those axes there. All right, start walking through these one by one. Let's start with this bottom one in the middle. Guys, this bottom one in the middle. Mass as a function of time. So what this could be is maybe you have a lightweight car, a kind of a medium car, and like a really heavy car. You guys remember you could tape on lab weights? Some of you guys were doing that. Probably about 30 guys taping on lab weight. Okay, so as the mass was changed, and this one maybe it's kind of backwards in terms of independent dependent variable, right? But if you guys remember, if time is ever ticking along as a rule, you always put time on the horizontal axis. Okay, but you could have different mass cars. How would that affect how much time it took to go some set distance? Go ahead and draw that graph in the bottom middle. Okay, that's the first one I'm going to be walking around looking at. Okay, so yeah, the bottom one in the middle. You guys all drawing this graph? Okay, you guys drawing this graph? The bottom one in the middle, mass versus time. What does that look like? Mass versus time. What would that graph look like? Mass versus time. Right here, no relationship. No relationship. So you can have different mass cars, but they all take what, the same time travel distance, which makes this graph look like what shape? Wait a minute, guys. If you said horizontal, what that would mean is that you're using the same mass car over and over and over, and you're getting completely different times for the same mass car. Huh? Vertical. Guys, vertical here means you're using lots of different mass cars, and it's all the same time. Isn't that what that would mean? You can plot a bunch of points and line up like that. Next one. Let's jump over to velocity versus time. All right, this one here. So some guys had the speed gate, and yes, you're letting it roll different distances so that it could roll for different amounts of time, but you're specifically recording how fast was it going as a function of the rolling time with the stopwatch. Okay. Guys, what does this graph look like right here? Yeah, I guess say linear like that. Okay. Because and guys, what does the slope of that graph represent? Acceleration. Okay. Well, what other property could you get out of that graph?
The area under it. the area under the curve, which represents, yeah, displacement, how far the car rolled. That could be, right? All right. Let's hit this bottom right one. What does acceleration versus time look like then? Yeah, just flat line. So constant acceleration, which is the slope of v versus t, which is also constant, of course, because they go hand in hand. Okay. All right, let's hit this top right one. How about how far did the car roll as a function of time? Some of you guys had a meter stick and a stopwatch, and you recorded, say, after half a second, 1 second, 1.5, 2 seconds, like how far did the... Yeah, you guys got... All right. And what's the basic equation of that? X equals what? 1/2 at squared. Yeah, x is 1/2 at squared. There you go. All right. Okay, so speaking of distance and time, there's another graph I have same variables. Is this one right in the center? You guys see distance versus time squared? Okay. Yeah. You guys are saying linear? Right. Now, guys, what is the slope of this line? X versus t squared. 1/2 a. Yeah, 1/2 the acceleration. Whoops. Okay. All right. And here's the last two. So velocity is a function of distance. You got square root relationship, and then if you square the velocities, v squared is proportional to distance. Okay. Okay. Don't all those graphical relationships lead to those three kinematic formulas? You guys know that's what this is all marching towards, right? Pretty soon. Oh, actually, that is the next slide. Kinematic formulas. All right, guys, ready? You guys got all those graphs? Okay. You guys know, of course, this file I just posted on Google Classroom last night, so you guys can download the whole class. All right. Guys, go. The next slide is the three kinematic formulas. Go ahead and write down the three kinematic formulas. Hey, yes, they're on the AP equation page, so technically you don't have to memorize it, but if you do, it'll save time, and it's probably better for your brain anyway to know. And we use them over and over and over. You probably memorize them just using them over and over. Do you guys know the three kinematic formulas?
Yeah.
All right. Let's start with the one in the middle. What's the one in the middle? Yeah, and you can see the units on this one too. Okay. You guys see meters per second, meters per second. You guys, what is meters per second squared multiplied by seconds? What does that give you?
Meters per second.
Also meters per second. If you had different terms together, guys, different terms, if you want to add them together, do they have to have the same units? Who says they do? Who says they do? Yes, they have to have the same units. You guys see that here. What's the top one? Top formula. There you go. Right. And how about the last one?
Final squared, squared, so it's 2a.
They said that right there. All right, and then here's with the strut. Okay. Guys, how many unique variables do you see on that page?
1, 2, 3, 4, 5.
5. Yeah, there's 5. Okay. And to be able to solve any of these in an accelerating situation, suppose there is acceleration. How many different variables do you need to solve? Yeah, you need to identify 3. Yeah, identify 3. Okay. Or if acceleration was equal to 0, then that could be a known. And then, because if there's no acceleration, there's only one formula that really matters. Isn't this top one just x equals vt? That's like cruise control. You're going on a car trip. Yeah, constant speed. Okay. All right. Okay, so no any 3, solve the other 2. Could have you guys solve that, but you could get that. All right. Ooh, speaking of cruise control, going on a road trip, car's driving constant velocity. Let's say you hit I-95 and you're just driving straight north, just cruise control. Right. Do that for a few hours. Right. Draw those 3 graphs right there. Those 3 graphs. All right, see how you guys are doing that here. Constant velocity. That phrase I just said, constant velocity, it should tell you exactly what this middle graph looks like. What does that look like? It looks like velocity that's constant. That's constant velocity. So if you look at your speedometer, maybe your speedometer says 70 miles an hour, 70 miles an hour, 70 miles an hour. It's not changing. You'd be driving 1, 2, 3 hours. It's just stuck at 70 miles an hour. How about how far have you traveled? Sorry, that's not the next one I have. Let's do acceleration. Guys, what's the acceleration of this thing? Yeah, zero. Zero acceleration. Oh, yeah, it's right there, isn't it? Yeah. Because zero acceleration, constant velocity, those go hand in hand, right? If I say one thing, it's synonymous with the other. Okay. How about how far have you traveled as a function of time? What does that look like? Yeah, there you go. Right. So after 1 mile, you traveled, sorry, after 1 hour, you traveled 70 miles. After 2 hours, 140 miles, and so on. 3 hours, 210 miles. Okay. Oh, and then, guys, we got properties. Right. That slope at x versus t tells you velocity, and the area under curve v versus t tells you how far you've gone. Those also go hand in hand. Right. I think you guys said that earlier. All right. All right. Can you feel how fast a car is moving? Can you feel 70 miles an hour? No, you can feel speeding up, braking, or what's the third thing? There's speeding up and braking. What's this one on the bottom right? Steering wheel, right? Which we didn't actually talk about for a while, right? Not until we got to, well, a few weeks later in the semester. Right. So you guys know speeding up, braking, and then steering wheel. Right? Those are the three things you can feel in the car. Got linear acceleration, centripetal acceleration. Right. All right. Let's go through this table. So drop a ball off a cliff. This might be a lot to write, but I think you guys know these numbers anyway. So let's do the presentation version of these. All right, so it's right after you release the ball. I know it says time zero. Let's say it's like 0.001 seconds. So you just released it. Okay. What's the acceleration? Yeah, you can say 9.8 or 10 meters per second squared. Right. Now for this table, I'm just going to use 10 because it gives not really nice round numbers. Right. After 1 second, what's the acceleration?
10.
10 meters per second squared? How about if it's 2 seconds?
10.
Yeah. Right. Okay, so yeah, assume no air drag and gravity of the planet, it's 10 meters per second squared. Right? So that could be, like, say, after 5 seconds, it's like a millimeter above the ground, still accelerating that much. Okay. All right. How about if you, did I say the word drop on? Oh, yeah, there it is, drop. Guys, as soon as you see the word drop, what does that tell you about initial velocity? Yeah, zero. So start with zero. Okay. How about after 1 second, it's picked up to what?
5.
Huh? Hold on, careful.
Sorry, I was 10.
Yeah, let's go back to. Oh, this is as far back. Right. You guys know these formulas can answer that whole table, right? And so this middle one right here, if you take 0 plus 10 times 1, we'll do 0 plus 10 times 2, 0 plus 10 times 3, 10 velocity. Right? Now that last column I haven't hit yet. It's something about how far is the ball fallen, and that's x is proportional to t squared. Okay, so we're gonna say, all right, let's go back to the table here. Boing, boing. Okay, so you guys know the velocity picks up 10 meters per second per passing second, 10, 20, 30, 40, 50, right? Okay, and I'm going to define the top of the clip as 0.0. Okay, and the question is going to be how far has the ball fallen from there?
5.
Yeah, here's your 5 right here. Here, 5 meters, 5 meters. You guys know, of course, all these numbers have units attached to them, which I embedded in the title column, or the title, right? So meters. That comes from 1/2 AT squared. So 1/2 times 10 times 1 squared. Okay, 5 meters. Okay. How about after 2 seconds? How far? You guys got calculators, right? Do 1/2 AT squared, run 2 seconds. What do you get? 20 meters? Yeah, 20 meters, 3 meters.
No.
3 seconds, how far? 45 meters? 4 seconds, how far? Huh? 80? All right. Pause right here because you guys say from 2 seconds to 4 seconds. Isn't that double the amount of time from 2 to 4? Right. And 1/2 AT squared, if you square the t and you're doubling the t, guys, what is double squared? It's a factor of what? 4? Right. What's 4 times 20? 80. Right. So proportionalities. Okay. And finally, it's been falling for 5 seconds. Yeah, it's about 145 meters deep. How'd you know that? College. Yeah. So you guys got Cliff? No, guys, when you get the AP exam, every once in a while they actually flip this upside down. So they'll define the top of the cliff as 125 meters above sea level. And then they'll say, what's the height? And then could you guys do reverse and have 125 up here? And then work your way to figure out, get to 0 at the bottom? Do that. Right. Guys, if that was the case, if AP turns this whole thing upside down, which they do sometimes, and if it starts at elevation 125 meters,
Where did we start?
what's the elevation after 1 second? Huh? Guys, what's the elevation after 1 second?
How high is the cliff?
Huh? You're saying 120, right? 120? Because it'd be 125, and then down 5 would be 120. Okay. Okay. All right. Can you guys draw the graphs? Okay, so you saw the full table of values. Okay, you can pull out 3 graphs out of that. Go sketch this graph real fast.
These are ones that
Yeah, you guys have seen these new maybe 100 times by now in this class. I wouldn't be surprised to see these graphs at least 100 times by now. All right, so let's start with the middle one. What did you guys draw for velocity versus time? Yeah, linear. Let's jump down to acceleration versus time. What did you guys draw? Constant value. Yeah. For gravity field of the planet, yeah, and on Earth that would be about 10 meters per second squared. Okay. And what shape did you guys draw for x versus t?
absolute
Yeah, parabola with the vertex starting at the origin. Okay. Yeah, this is all. There's no air drag down to the positive direction. We're starting at point 0. That's all that. Right? Because remember too, AP could totally turn these all upside down. So if you define the bottom of the cliff as point 0 and it starts at the top, what would you do to this x versus t graph? Yeah, flip it upside down, wouldn't you? Okay. So the vertex could be up here, and otherwise it's just upside down parabola. Okay, couldn't that be the case? And then all right, there we go. We got the slope of each graph represents the rate change. All right, these are all linked. Guys, what branch of math is that right there in red? What branch of math talks about rates of change? Calculus. Okay, that's calculus. Okay, I think about half you guys in calculus, right? Everything in red, that's derivatives, isn't it? Okay. And now let's go the other way. What other property could we be talking about? Yeah, integration, area under the curve, which tells you something about the change in the graph above it. Okay, so these are all connected. If you know one of those graphs, you can kind of figure out what all the other ones look like. Okay, guys got all that?
Yeah.
All right. All right. How about this? What about, let's keep all our conventions. Let's call the top of the point 0 like we've been doing all along. Let's define down as positive like we have been also all along about the side. Okay. But now we got two scenarios. What if you throw the ball upward? What if you throw the ball downward? Again, sticking to the conventions we've been using for the last few slides. So down is positive, top becomes point 0. Give you guys a little visual right there. All right, what do those graphs look like? Throw a ball, upward, throw a ball, downward. Okay, so piecing those together, maybe throw you guys some hints or how to frame these or think about them. Okay. I know if I throw the ball upward, does it eventually change direction? Yeah, because it's going to go up to some maximum height. It's going to turn around. Huh? How could I show that on these graphs? Right? What if I throw the ball straight down? Does it ever change direction in that case? No, it's already on the move and then it just goes faster until it finally crashes. Huh. How does that show up on these graphs? Huh. Not sure. All right, so start with this left one in the middle. What did you guys draw for this graph right here that I'm circling? What do you guys draw? Yeah. Linear starting from a negative because guys, if we're defining down as positive, but you throw the ball upward, aren't you throwing it in the negative direction? According to just how you define this. Again, AP could always turn that upside down. Right? Right? All right, that's why I put V naught right here in the negative territory. Right? And the rest of this graph looks like what again? Yeah, just linear. Okay. And that has a slope of what? Yeah, the acceleration, which is the gravity field of the planet. Yeah. Okay. Guys, this point that I'm pointing to right here with my mouse cursor, what does that represent in terms of the motion? Yeah, the peak. Right. That time right there corresponds to the maximum height, doesn't it? Right? Like the area of this little triangle right here corresponds to maximum height, which may tell you something about this x versus t graph, right? Yeah, let's call the top of the cliff point 0. So go ahead and put a point right at the origin, right there, right at the origin, right? And then what? What's the rest of that graph look like? Okay, yeah. You guys hear Justin? Guys, something about a parabola, right? And remember, these graphs are sort of upside down over because I'm defining down as positive, so up is negative. Okay. If down is positive, up is negative. You guys see that? Right. And here's another detail. Is look at that vertex right there. Does that represent like the maximum height vertex? How does that align with velocity versus time?
Same time.
Yeah, look at that, same time. Bing, right there, right there. Okay. Now, if you turn around and throw the ball downward instead, is it the same basic graph shapes? Same. In fact, I bet what you could do is you could take the graphs you already have. You guys, look where my mouse cursor is right now. And instead of throwing the ball upward, okay, so it's going up and then it's coming back down. If you just threw the ball straight down to start with, couldn't it just be these graphs like starting from this point right here? This point right here? Same thing? Here. Boing, boing, boing. Okay? And one more detail. Guys, is the vertex of this parabola shown in this graph at all? No, I don't see a vertex because yeah, it was initially already on the move. So the slope of that would represent the initial velocity. Yeah, hop hops through it. Yeah. Oh, actually, no, I do have another detail. Oh, let's look at this velocity versus time right here. What shape is this underneath this curve?
It's like a rectangle and a triangle.
Yeah, rectangle and a triangle. Yeah, it's a trapezoid. I like the rectangle and triangle though because it breaks it up. Into that. Let's see. And what does that green area represent again? Yeah, distance moved or displacement or distance, right? So see, distance could be there's v naught t plus 1/2 gt squared. Hey, v naught t plus 1/2 gt squared. Yeah, that's that kinematic formula. Oh yeah. Oh yeah. All right, so this next slide, I just got that blown up. Boom. Boom.
Wow.
Boom. There you go.
This is why we do it.
So velocity versus time. Okay. So this accelerating, constant acceleration, so uniform acceleration. Maybe you threw the ball downward. Okay. V naught t plus 1/2 at squared. Slope is acceleration. It's all there. It's all there. Derived reaction time from scratch. Go. Remember, if they see after this, suppose this is a part of a larger FRQ, they would want you to start with an equation or some version of an equation from that formula page. It could be a short version. But you're allowed to get anything from the formula page or know anything from the formula page. And then you have to do a little algebra rearrangement. And hit that last line, the reaction time is something. No, maybe memorize the answer, which couldn't hurt you. I mean, it could be okay though. But if you just write down the answer and they don't say where you derived it from, they would not give you full credit. They want you to start with one of your basic equations from the formula page and do a little algebra derivation to show like, yeah, see where that comes from. So go ahead, take a trek around the room. Who's solving reaction time? All right. Okay. Lily got it. Chloe got it. Yeah, Justin got it. Guys, oh yeah, I was there. See. Okay. Yeah. Okay, you got it. Got it. Okay. Well, okay. I'm not looking for. Guys, I'm not looking for speed. I'm looking for reaction time. Yes, Samantha got it. Okay. How about anybody over here?
Wait,
Yeah, Dominic got it. Oh, just send your square root.
you already on that.
They missed a couple of guys, but hey, some of you guys are getting this. Okay, so guys, what formula did you guys start with? Yeah, it's that first kinematic formula. Now, this is a shortened version of this. You guys know the full version goes x equals v naught t plus 1/2 at squared. But you're not throwing the ruler down, you're just dropping it. So you can get rid of the v naught t part, that just goes to 0. Okay. And maybe the x will change to an h for a height change. Okay. So h is 1/2 gt squared. So you can start with that. Yeah, it's a simplified version. Oh, okay. And you're solving for t, right? Solving for t. Right? So say I'm gonna cross multiply the 2, divide down Earth gravity. That's t squared. And then last step is to take the square root. Okay. You guys, one thing I saw too as I was walking around. Guys, look at the square root. Do you guys see the square root clearly includes the 2, the h, and the g? Do you guys see that? Okay. No, throughout the semester and also just now, see, sometimes students don't have everything under the root, right? Like they might stop the root just over the 2 and then the h is hanging outside it. Or they'll just put the root over the numerator and they forget to include the g. Okay, so have the whole expression in there, the whole expression. Otherwise, they're gonna dock points. Okay. You guys can drive that. All right, guys, good. Guys, good. All right, guys, close to the left. Ooh, car brakes to a stop. Car brakes to a stop.
does in fact break.
So on in your notes, right? Car brakes to a stop. Get those 3 sets of axes. Draw those graphs. Car brakes to a stop.
I gotta put this in.
Say, well, if it's braking to a stop, what's its final velocity? 0. Right. So after some time's passed, it's going to 0. But it would have had an initial velocity, right? Right. So start with this middle graph. Guys, what does this middle graph look like?
Downward.
Boom, just like that. Right? And okay, so that's like velocity point for point for point. Maybe it takes a few seconds to break to stop. Okay. It's what does the slope of that graph represent? The acceleration. Aha, bam, right there. Okay, that also tells you the third graph. Okay. It's a constant negative value. Hey, constant negative value. Oh, how about the area under the curve? What does the area under the curve represent? Yeah, the distance, the braking distance. Right? And if you break this up into, suppose it took 3 seconds to brake to a stop. Looks like during the first second, the car went a long way because it's traveling so fast. In the second second, not as far. In the third second, it moved just a little bit because it's going so slow at that point. Okay.
That's what I need.
Here we go. Oh, here we go. So this is the full thing. Full thing right there. There.
They did it the opposite way. Like, how do you go negative? How do you go backwards? You have to keep going backwards. We're going backwards now. Because it was stuff. You're still going. Stop. Stop. I looked at your graph. I'm like, huh? No, because he's actually going backwards. Yeah, he's an exactly. Put his car into reverse and goes backwards. That's the best way to stop. Yeah. If I was doing it from a different spring.
Oh, yeah. That's a good thing to point out, right? If the car's braking to stop, it is still moving forward. It's always moving forward, right?
Yeah,
Always moving forward. Never actually.
Put a finger first, and then you can put it first, Gary.
And guys, is this a parabola right here? Is that a parabola? Yeah, that's a parabola. Where's the vertex? Yeah, right at the end point. Right at the stop point. Okay. All right. Let's pair velocity and acceleration. So, guys, what if velocity is positive and acceleration is also positive? What does that mean is happening to the motion? Yeah, you're moving forward, well, in the positive direction. I'll call it forward. Moving forward, speeding up. Okay. Moving forward, speeding up. Okay. How about negative? What does that mean?
Slowing down. Moving back.
Sure about that?
No, speeding up, moving backwards.
Speeding up, moving backwards. Okay, guys, the direction of your motion. What tells you the direction of your motion? Velocity or acceleration? Velocity. Velocity tells you the direction of your motion. Okay, so yeah, so it is backwards. And if the signs match, like negative and also negative, that means anytime the signs match, you're always doing what? Like speeding up? Yeah, so moving backwards, speeding up. Okay, let's hit this bottom left. What if you have positive velocity and negative acceleration? What does that mean?
Moving forward, slowing down.
Hey, is that what you just did for a car braking to a stop? The same thing. Moving forward, slowing down. That's a car braking to a stop. Finally, top right. What's this one mean?
Moving backwards, slowing down.
Moving backwards, slowing down. Right, I did that one last because I think it was a little heftier conceptually. All right, you guys got that. Got that. Yeah, let's go to projectiles. Projectiles. I think this may have been the first projectile I did with you guys. We got cannon PAL 50 meter per second at 37 degrees from the horizontal. Can you break these into components?
Sure.
Notice I'm saying in your notes right now you're drawing velocity vectors and velocity components. Right. We're not going to worry about forces yet. We're not at forces yet, which means that the diagram you're drawing, is this a free body diagram you guys are drawing? No, because you're not drawing anything to do with forces. You're just looking at velocity component, velocity and velocity components. Okay. All right, so draw that scenario right there. Okay. And at the instant the cannonball is leaving that cannon barrel, how? 50 meters per second at 37 degrees from the horizontal. Hey, 37 degrees. Have you guys seen that angle before? Yeah.
I wonder what the triangle.
Would you want to immediately break that into components, saying how fast is traveling across the field, how fast traffic traveling strictly upward? Can you guys do that? Guys, what components did you guys come up with for the last point? What are these components right here?
30, 40, and 30, 20. Yeah.
There you go. Right. And how could you get that on the calculator? What if the angle wasn't 37 degrees? How'd you get that on the calculator? Yeah, sine and cosine. So if you do 50 times sine of 37 degrees, that gives you 30 meters per second. If you do 50 meters per second times cosine of 37 degrees, that gives you 40 meters per second. Right, you guys do that? Okay. Now, from here on out, as the cannonball is traveling along this green curve, guys, is this green curve a parabola? Yeah, green curve is a parabola. Okay. What's happening to its horizontal component of velocity? Just the horizontal stays the same all the way across, because there's no horizontal forces. Right, gravity only pulls vertically, and we're ignoring air drag, so it's just gonna constant speed in the horizontal component. Right. Okay. Now, what about vertically? What's happening vertically? Is it on this slide? Is it slowing down vertically?
Yes.
Yeah. By how much every second?
10 meters per
10 meters per second every passing second. Which means after 1 second, it's kind of how fast strictly upward?
20.
20? Because 30 minus 10 is 20. And after 1 more second, how fast? 10 meters per second. And after 1 more second, that last little cannonball right there, yeah, 0 meters per second vertical, which would mean that it's reached its peak height. If I can see anything about peak height or something like that, that would be the physical variable to mark out. This vertical component of velocity goes to 0. Okay. You guys see that? And if you wanted to know the full speed of the ball, like if you point a radar gun at the ball right here, bam. Could you use this to calculate how fast that would be using Pythagorean theorem? Yeah, you could use Pythagorean theorem and put it back together to get the total speed. Okay? All right, next slide. Oh, here's the other half of this. The other half. All right. So let's do all the horizontal. What can you say about horizontal? 40 meters per second. Right, that never changed. Right? In that last frame, the cannonball is just above the ground level. Hasn't quite hit the ground yet. Right? How about vertical? What's this component right here? Yeah, so 10 down. Yeah, you can say negative 10 meters per second. You can do that. If down is negative now. Right? How about right here?
20.
And how about right here? 30 meters per second. Okay. And since this cannonball is just above the ground, what can you say is the crash speed? 50 meters per second. You use a Pythagorean theorem, put it back together. Right? Or you can say by symmetry. If it started at ground level, yeah, no air drag is an important aspect too. Yeah, no air drag. Right? Started at ground level is blasted 50 meters per second. Now it's going to crash at 50 meters per second. It's all the same ground level. Right? All right. Did you guys use? Actually, you guys just did this and this, right? You guys just did those vector components. So you just did that.
Wow.
All right. Let's go to edge of a cliff. Ooh, do you guys remember taking those launchers out to the balcony? You guys remember that? Okay. Now the green is like how far has it traveled across? That could be the blast speed times however much time. You guys, this time, isn't this the time of fall? How much time it takes to fall down? Okay. And that has something to do with the height of the cliff. So how far it moves, y, it's 1/2 gt squared, and then finally it'll crash into the ground. Right. Okay, so this distance is a function of time for horizontal and vertical. All right. Let's do last distance from the edge of a cliff. Okay, so guys, we're going to go through a whole procedure, and the last step is to say this distance equals something. Let's say you're allowed to know everything else. Let's say you're allowed to know the blast speed of the cannon. You're allowed to know the gravity field. You're allowed to know the height of the cliff. You're allowed to know everything except for this d, this horizontal distance, and you're going to solve for that. I can throw you some numbers because the gravity field is 10 meters per second squared. If you say the height of the cliff is 4 meters or 5 meters, whatever. I could. You're allowed to know you blast the cannon straight horizontally, so it matches the picture.
Solve it. Solve it.
All right. Let's start with the vertical, guys. What vertical equation did you guys write right here? Yep, it just copy pasted it from right there. H is 1/2 gt squared. Okay. Now we're gonna go through a series of algebra steps. What do you guys think we're headed towards? We're gonna solve for what?
T.
T. Yeah, we gotta, because if you know the height of this cliff, you gotta figure out what the resulting hang time is gonna be. Can you guys solve for T?
The reaction time equation.
It is. It is the reaction time equation. That's why. That's why I had to do that one earlier. Yeah. You guys are dropping really for the friends. Hey, what's the horizontal equation here? Yeah, just copy pasted that green right there. The Vx is the D blast it, as long as you blast it horizontal, which you guys were doing. Now what? Now what?
Substitute in T.
Aha! Substitution. And there's the blast speed based on the height of the cliff and the gravity field of the planet. Boom, boom. Okay, you guys can do that. Yeah, I gave you guys some numbers. So if I said the height of the cliff was so many meters and the gravity field is like 10 meters per second squared, right, and the blast speed of the cannon. Right, if I gave you all that, you just feed it into that expression, you got it. Right?
That's all. You see how we would do
Right.
with one day.
All right, next slide. Hey, it's the same picture. Oh, but we're solving for something different. This was actually your guys' lab. You guys remember I wanted you to figure out what is the launch speed of those launchers? Okay. Because realistically, couldn't you take either a meter stick or a trundle wheel and measure how far did the bouncy ball land from the edge? Right. That was a much easier number to grab. Okay. And you guys are going to back calculate what was the blast speed of those launchers. Okay. What's the blast speed of the launcher? So go ahead, write as much as you can. What do you remember here?
I just move it over. Yeah. We have our original. Move it over.
All right, let's start with vertical. What did you guys write for vertical? Yeah, same as the last slide. Same formula, rearrange it, solve for T. Got it like that?
No.
What did you guys write for horizontal?
E equals U blast time. The same.
Yeah, T equals BT. Also the same as before. So actually, most of this is really the same as the last slide. Just what you're solving for is B blast instead of D. Okay, so I'm going to rearrange this how? Yeah, remember we're solving for V blast, so it's got to be a D over T, whatever this distance is.
Wow.
Right,
This is insane.
what's next?
17.
Sub and T? Okay. So, guys, notice you're dividing by a square root and a fraction. Because if you're dividing by a fraction, are you allowed to take that fraction and flip and multiply it? Multiply by the reciprocal? Right. So that brings us to the last box. Go ahead and write. What do you think that last box is going to be? You guys to digest that and make a prediction. What's that last box look like? All right, what do you guys write? Yeah, I'd write it like that. Now, if you left it as a fraction within a fraction, then AP would still accept that too. Okay. So you get it. Okay. A couple ways to write that. All right. And of course, you guys did lab on that. Ooh. This is a fun one. I forget if we covered this in class, but I suppose this guy's going to release the arrow at the exact same time the apple starts falling from the tree. And he wants to hit the apple with the arrow before it hits the ground. Right? Should he aim? Where should he aim? Above the apple, at the apple, or below the apple? Show hands. How many guys say that he should aim above the apple? Who says at the apple? Does anybody say below? All right. Should aim right at it. Right at it. Okay. And the idea is that again, if he's releasing the arrow at the exact same time the apple begins falling, right, that they're both gonna have the same vertical displacement due to gravity. Right? So this delta H is the same for both. And hence the arrow will hit the apple. Okay.
No.
All right. Range formula. All right, so how far will this cannonball land as a function of blast speed and angle? Angle also. Okay. So let's start with vertical. Vertical. There's actually a couple of different ways to do this. There's the first kinematic formula. Guys, if you use the first kinematic formula like I did here, what is the vertical change from the ground to the ground? What's the vertical change?
0.
0. Isn't that where that 0 is coming from? Starting at ground level and ending at ground level? 0. Great. I mean, everything else follows there. And let's say I'm going to solve for t. Right, a little switcheroo here. Now horizontal, which is really what we're solving for. I want to know how far does this cannonball land downfield? Can you guys say x equals vt? Okay. And the v is really the horizontal component, so it's the blast speed times cosine theta. T. All right. Now, guys, can you take this t right here and sub it in for that t right there? So we're going to substitute out the time. So you don't need a stopwatch necessarily, as long as you know the blast speed and the angle. You don't need a stopwatch. You're going to substitute right there. And it's going to look like that. Oh. Okay. Which cleans up like that a little bit. Does anybody remember from a math class something called a double angle identity? Yeah. All right. Lily remembers this. You guys remember like sine of t theta is 2 sine theta cosine theta? Okay, show of hands. How many guys does that ring a bell from math class? Yeah. A lot of you guys remember this? It's like, oh yeah. Okay. You can actually take advantage of that right here. Notice they put this in brackets. Boink. Boink. There you go. Okay. So
But better than not, yes.
how about how about you're in a baseball throwing contest with your friends? Can you change your maximum throwing speed? I think your maximum throwing speed is just whatever it is, right? But you can change how you throw the ball. How? What can you change? Yeah, the angle that you throw it. Okay. So if the competition is who can throw the ball the furthest, maybe I could start with this that you guys are looking at. Right. But the question is, what's the optimal angle to send the ball the furthest? Do you guys know what the optimal angle is? Well, if you throw it at, yeah, you said 45 degrees? Yeah, right. If you throw it at 0, it doesn't go very far. It just hits the ground almost immediately. Okay. Guys, anytime you see the word optimal, what branch of math do you think you need to solve that? Yeah, calculus. Okay. Because what you got to do is, this is a little bit beyond this class. AP is obviously not going to ask that for this class. Okay. But that's how you solve that. 45 degrees.
Oh, no.
All right. I think that, yeah, that takes us to the end of kinematic. Hey, so guys, tomorrow we'll do some dynamics. Are you guys ready to make some free body diagrams tomorrow? Yeah. And then I'll get you guys your quiz on Thursday.